Hello everyone, how is your day? Today, we have to tackle about the electromagnetic wave. I am Riellen M. Amandaron together with my co-reporter Carl Justine L. Riingen. First, we have the Maxwell equation and electromagnetic wave. Second, we have the plane electromagnetic wave and the speed of light. Third, we have the energy and the momentum electromagnetic wave standing electromagnetic wave.
Electromagnetic waves, or EM waves, are waves that are created as a result of vibrations between an electric field and a magnetic field. In other words, EM waves are composed of oscillating magnetic and electric fields.
Now we have to tackle the Maxwell equation and electromagnetic wave.
According to Maxwell, electromagnetic waves resulted from his formulation of a complete and symmetric theory of electricity and magnetism known as Maxwell's equations.
Now we have to tackle the plane electromagnetic wave and the speed of light. Do electromagnetic waves travel at the same speed of light? Generally speaking, we say that light travels in waves. All electromagnetic radiation travels at the same speed, which is about 3.0 or 0.8 meters per second through a vacuum. We call this speed of light. Nothing can move faster than speed of light. Why do electromagnetic waves travel at the speed of light? What distinguishes this different band of light is their frequency, or the wavelength. But what they all have in common is that they travel at the same speed in vacuum. The reason for qualifying in vacuum is because EM waves of different frequencies often propagate at different speed through material. And the last one is the energy and the momentum and the electromagnetic waves standing in electromagnetic waves. We have to watch this video to understand more about this.
We can easily calculate the energy and momentum of EM waves. And in this section I also introduce a new quantity called intensity. Hi, this is Jonathan Gardner. We're in section 822 of Griffith's Introduction to Electrodynamics, 2nd edition. We just figured out how monochromatic plane waves behave in a vacuum, and how to calculate the EMB fields at any given point in time for a given wave of specific frequency. Now we're going to look at the energy, momentum, and introduce the concept of intensity. Keep in mind, what follows applies only to monochromatic plane waves. There are other types of waves, and we're not talking about them. So when you do your spherical wave homework, it's going to be a little bit different. But it's a very easy process, so you should be able to read arrive everything. U, the potential energy, the energy of an ENB field, is 1/2 of epsilon naught E squared plus 1 over mu naught B squared. Very simple. So we have the relation that our B field is whatever the E field is divided by C. That's what we derived earlier for an electromagnetic wave. And so that's just the square root of mu naught epsilon naught of E. Plug that into here and we get 1/2 epsilon naught E squared plus B squared, which is, it's going to be something E squared. So we're going to have a mu naught on top and an epsilon on top, and the mu naughts cancel, and so we have epsilon naught. And so look at this. This is interesting. The amount of energy stored in the E field is the exact same as the amount of energy stored in the B field at any given moment in time. Okay? And the total energy is just epsilon naught, whatever the electric field is at any given moment in time. As we saw, the electric field and magnetic fields are at their maximum together, and when they're zero, they're both zero together. And so we have a situation where, looking at a wave, a snapshot of a wave, as we move along the x-axis, we're going to see some spots where it's maximum energy and some spots where there's zero energy. Also, if you stand at a certain point and let the wave pass by you, you're going to see the energy increase, decrease, hit zero, and then increase again, and then decrease and hit zero. Let's write out the equation for that. So E squared is, we're going to have epsilon naught. What's E squared? That's or epsilon, or E naught. I just realized I did something wrong in the last video, but it's a tiny mistake and you'll catch it. Cosine squared of kappa x minus omega t plus delta in the n hat direction, but we don't care about n hat direction, so ignore that. Okay, that is the energy at any given point in time or space for a monochromatic plane wave. What's next? Then we have, oh, I should probably draw a graph so you understand this better. U, X, T, whatever. So it's going to go, it kind of makes this weird. This is just, you know, epsilon not E squared, E naught squared, whatever that is. Okay, next we have energy flux density, the pointing vector. So S vector equals 1 over mu naught. I remember a previous video where I forgot that factor and everything was stupid. E cross B. Okay, so the energy flux density, the pointing vector represents the energy flux density, the rate of energy passing through a surface at any given point in time. So E cross B, what does that look like? Well, we have that these are two perpendicular fields. They're always perpendicular to each other. So we just take the magnitudes and multiply them by each other in the direction. If you take E cross B, so E cross B, for instance, will give you the direction of motion. So we have 1 over mu naught E naught. I'm just going to write it out here just in case anybody doubts me. And then 1 over C E naught kappa x minus omega t plus delta. And the direction is in the direction of motion. Let's say we're going in the x direction, so it's the I hat. Okay, so 1 over mu times 1 over c gives us c times epsilon. E naught squared, cosine squared, kappa x minus omega t plus delta. And well, E naught, epsilon naught E naught squared is just c times the potential energy pointing in the I hat direction. That's all it is. So S vector is the speed of light times the potential energy, which we derived moments before, pointing in the direction of motion. Okay, so here again we have the energy flux density. So the energy is going to quickly, at the maximum, it's flowing very quickly. At the minimum, or at zero, when the E and B fields are zero, there's no flux density passing through. So the next interesting thing is momentum. Remember, momentum we discovered was P vector was just 1 over c squared times the S vector. We just calculated the S vector. So that's going to be 1 over c u I hat. That's the momentum of the wave. Once again, the momentum of the wave has a maximum and a minimum of 0. And notice the momentum never points backwards. So because we're taking the squares of the fields here with the u. So there's this curious relationship. The magnitude u is equal to the magnitude of the momentum times c. And if you are familiar with relativity, hopefully you are, it should be no surprise because E squared is equal to PC squared plus MC squared squared, right? So, of course, the energy is PC of light. It has no mass. So, that's curious. It's one of the things that helped people accept Einstein's theory of relativity as possibly being true. The next thing I want to talk about is the average over. So if we take a complete cycle and average what these values are, or if we wait for many, many cycles and see what the average of the values we record are, and if we're waiting many, many cycles, we don't have to have an integer number of cycles. We can include the tail end of a partial cycle, and it's not going to throw off our results by very much, if at all, especially if we're taking billions and billions of cycles, like we would in a real laboratory. Okay, so the average of cosine squared, 1 over half of epsilon E naught squared. So the 1/2 comes from the fact that the average of cosine squared is 1/2. And then the average of S vector, yes, the average of S vector is 1/2 of CU, well, the 1/2 is already in the U, so C times the average U in the I hat direction, and the average momentum is just 1 over C, the average of U in the I hat direction. And so the bracket notation hopefully isn't foreign to you. The reason why we're talking about average all of a sudden is because I want to introduce intensity. Intensity is simply the average of S, the magnitude of the pointing vector. And so in the case of an electromagnetic field, the intensity is simply 1/2 C epsilon naught, the maximum electric field squared. That's the intensity that we get. So the intensity is useful because it tells us power transfer. It tells us how much power is being transferred. This is a very easy section. I hope you don't get too confused by it. Take some time to memorize some of these so that when you'll recognize them when you see them and you won't get stumped on a test. So thanks for your time. Oh, if you have any questions, comments below. Thanks. Bye. Oh, like and share with your friends too, please. Thanks for your time. Bye.
Thank you for listening, guys. Keep safe and God bless.